Welcome to Green Giants, Titans of Renewable Energy, the podcast where insights and innovation meet. Every episode, we dive into conversations with industry leaders, experts, and change makers, bringing you the stories and ideas in the renewable energy sector that shape our world. And now, let's jump into today's episode with your host, Wes Ashworth. Welcome back to Green Giants, Titans of Renewable Energy. Today, we're joined by Will Regan, founder and chief scientist at Pacific Fusion. Will has spent nearly 20 years working at the edge of energy innovation, from ARPA-E to X, Alphabet's moonshot factory, where he helped create the original vision and team behind Mineral. Today, he helps lead Pacific Fusion, one of the most ambitious companies working to bring fusion from scientific milestone to real-world clean energy infrastructure. The big theme today is simple. Fusion is no longer just a distant promise. It's entering a new chapter focused on engineering, manufacturing, and real-world execution. With that, Will, welcome to the show.
Thanks, Wes. Great to be here.
It is absolutely great to have you. Fusion is one of those fascinating topics that I feel like everybody's really hungry to know more about. So this is very timely and excited to get into it. But we'll start a bit with your story as we always do. And as I mentioned there in the intro, you've spent your career really around solving these hard, complex problems. What's the thread that just connects all of those chapters for you?
Yeah, I think the common thread is I've always tried to be working towards sustainable abundance. So the most positive with the least negative. More energy, more food, more quality of life with the lowest amount of cost or pollution or materials or land. And when we make it work, fusion has the potential to do that, to give you that global optimum for energy.
Yeah, absolutely. I like the way you frame that. It's a cool way to frame it up and put it, and I think gives listeners a sense too that this path has not been random. There's clear through line and clear intention there. And you've said you started even in solar, maybe around the first sort of clean tech boom and bust, just as solar costs were falling faster than many people expected. How did watching solar move from technical problem to deployment problem just shape the way you think about fusion today?
Yeah, I think it was instrumental in shaping the way I approach fusion, the way we approach it here at Pacific Fusion. I think it's understanding the learning curve and the benefits of modularity, of having a small unit you can iterate on quickly to drive costs down and learn quickly. But that's a key feature of what we're doing at Pacific Fusion, is making our system as modular as we can.
Yeah, and it absolutely such an important lesson. I think technologies can also just shift from impossible to inevitable faster than people expect a lot of times as well. And I think the solar comparison, kind of looking at that, really helps and shows how quickly energy technology can move, once the cost curve starts working. As again, it highlighted in the intro at ARPA-E, you were exposed to just a wide range of energy technologies and helped shape early fusion work. What did you see in fusion that made it feel different from every other energy pathway you evaluated?
Yeah, when I got to ARPA-E, I'd been working in solar before that, and I came in trying to take a fresh look at what are literally all our options. So there are these beautiful plots you can find, these exergy plots of the world. All of the energy flows in and out of the earth, and you can basically say, this is the sort of fossil category, here's the renewable category, wind, solar, hydro, geothermal, fission, fusion. And if you do these down selects of saying, what are the things that we have the most resource, that'll last us forever, that have the lowest impact on the environment, you rapidly down select to the things where you want firm power. That kind of limits you to geothermal, fission, and fusion are kind of the best options for those. And then when you go into, okay, what is the thing that can be deployed everywhere and has the sort of least amount of pollution, you end up in fusion as such an incredible opportunity. It's just we have to make it work. And we have something that will last us for millions of years of all of our energy needs.
Yeah, absolutely. The upside, huge when you talk about cracking that problem and what it can mean. And I think that perspective is really valuable because you were comparing fusion against a lot of other options, not looking at it in isolation. And, it makes sense why fusion stood out to you. Not just interesting science, just a different scale of potential impact. And, I would say obviously pick the problem that's really difficult to solve and needs to be solved as well too. So before Pacific Fusion, I mentioned there too, you spent years at X, Alphabet's moonshot factory, where you helped create the original vision and team behind Mineral. What did X teach you about just separating a real moonshot from just a seductive science project?
Yeah, I think one of the maxims that stuck with me there was fall in love with the problem, not the solution. So you really have to look at, what are you trying to solve? It's providing the most amount of energy with, the lowest negative externalities. And you have to do the things that will work. It's trying to provide the most energy with the least amount of material and land and pollution. That's effectively, what drove us to start this, is that fusion offers that potential.
Yeah, I like the way you're saying it. It sounds easier said than done in terms of falling in love with the problem instead of the solution. How does one actually do that? Any words of advice if somebody else is on maybe a earlier journey and having trouble with that?
No, I think, I've looked at a lot of different energy technologies, agriculture technologies. I think there's so many amazing things that people can work on. I like to, before really jumping into something, I like to sort of try to quantify what is the maximum impact this could have in its best form when you develop it, and and compare it against what's out there today. Because to matter, you got to do better than what's already existing at scale. You got to be lower cost or offer some other benefit. So, and I think you can often answer that question very quickly with just a few attributes of the thing you're pursuing.
Yeah, I like that a lot. Kind of fast forwarding to let's say around 2022, 2023, what changed? That made you say this is no longer a field to watch, but hey, this is a company to build. This is something a little bit more serious.
Yeah, I think major things changed that changed the fusion landscape in 2022, and it comes back to the question: what's it going to take for fusion energy to matter to really scale? You need to get energy out. That's sort of criteria number one. You need to do that to make a power source. But you also need to get there with a machine that can be built and run affordably. And the things that happened in 2022 were science and engineering breakthroughs that made both of those possible. Number one, that many folks have probably heard of, is the National Ignition Facility at Lawrence Livermore Lab achieved ignition. They used lasers to inertially confine and compress fuel and get it to burn, to ignite. And they got more energy out than they delivered to that little fuel can. That's great. The only challenge with that is the lasers they used are very inefficient. But that same year, there was another major breakthrough at Sandia National Laboratories on a machine called the Z machine. And they showed there's actually a much more efficient path to get to those same kind of conditions if you use electrical current pulses instead of lasers. So that's great. And they got the second highest performance ever. And then third, on the engineering side, that same year, a team led by our now CTO, Keith Lachine, demonstrated a new kind of modular pulse power hardware that lets you get to those conditions affordably with something that could be mass manufactured. So that was the foundation that not only is there a clear path to get energy out, but it's something that can be turned into a affordable, scalable power source. And that's why we founded the company. Yeah,
absolutely. It's amazing and kind of seeing that timing line up. And I'm always amazed that you get this small breakthrough and it's imperfect and it's not quite there. But then what comes after that? Just how many different breakthroughs that creates and causes after that. So that's incredible. And looking at that, so now we've spent a little time. We have the origin story. I want to make the technology more concrete. And a lot of people in clean energy, they understand solar, wind, storage, grid constraints, but fusion still feels mysterious. And so this next section is really about explaining fusion clearly, showing why Pacific's pathway is maybe a bit different. So for the clean energy audience out there that knows solar, wind, storage, and those sort of things, but may only know fusion from headlines, what is fusion in just the simplest possible terms?
Yeah, it's fusion is what the stars do. So it's funny. It's actually the most common source of power in the universe, right? It's what all the stars are doing every day. It's where you take very light atoms, typically hydrogen, and squeeze them together to turn them into a heavier atom, typically helium. And when you do that, you release millions of times more energy than in chemical reactions. And that's why it has such potential to be an incredible power source. If you can, when you make it work, it can be very, very power dense and energy dense, which means it has the potential to make very affordable power plants with low land and material requirements. The fuel itself is extremely common. It's hydrogen, water all around us, lithium that's, in seawater, in rocks and minerals. And we have enough of those materials on Earth to last us millions of years for all of our energy needs. And third, the other kind of important attribute is it's very clean. So it offers all those great benefits without the drawbacks. Fusion can't melt down. You have to keep driving it in order to make it fuse. It doesn't make long-lived, high-level waste, and there's no fissile material. So the sort of safety and proliferation concerns are much lower than fission.
Yeah, helpful explanation. Definitely makes it feel a lot more understandable, and that's a great starting point. I think that the physics is complex, so the basic idea is actually, fairly simple in a way. People often do hear about fusion. They immediately, maybe they do think of stars or billion-degree plasmas and science fiction, those kind of things. But what should they understand that makes fusion feel less mysterious and more like an engineering challenge?
Yeah, you can kind of use intuition from chemical reactions, but sort of multiply everything by a million. So to get fuel to burn, typically you need to get it hot, keep it together, and then it can start to ignite and burn. Same thing is true for fusion, except like a million times bigger. There's a metric in fusion that people typically refer to, and this is kind of the key metric that tracks progress towards making power sources, called the Lawson criterion. And that is the product of the fuel density, the fuel temperature, so how much fuel you have in a given space, how hot it is, and how long you keep the energy in once you heat it up. And if you get those three things, get it hot, and keep it together above a certain threshold, then you can produce net energy and power. So that's the main thing. And there's, Stars do this with gigantic balls of gas in space that unfortunately the gravity is too weak to make that a viable source on Earth. But we have multiple ways of getting to those conditions using either magnetic fields or inertia and sort of combinations of those.
Yeah, and we'll talk a little bit about one of those. It's specifically, Pacific Fusion is pursuing that pulse magnetic inertial fusion, or inertial fusion to put it simply. But in plain English, like, what does that mean? How is it different from other technologies? And as you said, sort of that laser driven approach that we talked about earlier. Like, what's different in your approach?
Yeah, so I mentioned there's two styles of confinement we've figured out how to do on Earth and gotten them very close to the finish line for getting energy out. There's magnetic confinement, which uses magnetic fields to keep the fuel confined to sort of a magnetic bottle, like donut-shaped chambers, like tokamaks that folks like Commonwealth Fusion. Or the other end of the spectrum is inertial confinement, where you take a little tiny pellet of fuel, little tiny capsule of fuel, squeeze it very fast, and get that small amount of fuel really hot and very dense, and then it burns. And that's more like, if a magnetic confinement system is more like a furnace that's continuously burning, inertial confinement is more like a diesel engine, where you put a little fuel in the cylinder, you squish it, get it to burn, get the energy out, and then repeat that process at some frequency. Now, in inertial confinement, there's a couple different ways we figured out how to get to those conditions. One is with lasers, and that's what many people are familiar with if they've heard about ignition on the NIF. But what we use is we call pulsar-driven inertial confinement, where we kind of cut out all the steps in between the capacitors and the fuel, and say we go directly from electrical energy stored in capacitors, send it along transmission lines, wires that bring it into the center of the machine, and that drives, goes right across the surface of our little fuel can and squishes it really fast. So it's a very, very efficient way of getting that energy into the fuel so we can get more energy out.
Yeah, absolutely. I think gives listeners a much clearer map of just the fusion landscape and the different technologies that are in play there and what you're doing. As we talked about a little bit, touched on briefly there, NIF showed the world that inertial fusion could cross an extraordinary scientific threshold. Where does Pacific's approach build on that breakthrough, and maybe where does it deliberately depart from it?
Yeah, there's a lot we can benefit from the laser-driven approach, the NIF style laser inertial confinement. That was the culmination of decades of research by many brilliant folks at the national labs and the fusion ecosystem, and all of the tools that they use to get there are very useful and important for us. So all of the sort of ways of making those little fuel cans, all the sophisticated diagnostics that are used to measure everything when you have a fusion event and understand exactly what happened. The simulation tools are also a really key tool that lets us do experiments, in simulation before we do them in the real physical world. So all of that directly translates to our system, and we've been fortunate to not only partner with the national labs that have done these breakthroughs, but many people who were responsible for those breakthroughs joined our team and are now doing it for us, like folks who led the experiments on the NIF that led to ignition and did the designs for those experiments. So that's a sort of a direct benefit we get from that. And then the other approach I mentioned, Sandia National Labs Z machine, that is kind of the direct predecessor to the technology we're building. So that uses those pulses of electricity and drives those small metal cans, squishes them, and gets them to those conditions. So we benefit directly from that approach too. So all of the learning that went into that, all the tools that enable both of those.
Yeah, absolutely. In Pacific specifically, you've talked a lited bit about this, but talked about modular pulsar systems, compact chambers, small targets. Help us understand a little bit better. And also, why does modularity matter so much if the goal's not just to prove fusion, but just to make it affordable and viable?
Yeah, modularity is really critical in two different ways. So one is manufacturability, keeping costs low. And, again, this is sort of, I learned this initially in solar of like, if you can make something small and iterate it on it quickly, you can improve much, much faster. There was an Oxford study that was done on 16,000 mega projects that have been built over the years and found that modular projects can be up to 10x lower cost and be built up to twice as fast. And that's because you can learn and optimize things on a small scale before you build on the big scale. Because you have more sort of copies of the same unit to build the system, you can come down your learning curves a lot faster, you get economies of scale faster. So that's sort of number one, is just lower cost, faster learning. The second part is more when we build fusion power plants, it lets us operate them much more reliably and at higher capacity factor. Because if your system is made from, say, 150 or 200 units, that are all contributing a little bit to the system to drive the system, you're able to service, say, one or two of those units while the system keeps running. You can unplug one of our modules, you can service it, plug it back in, and the machine has been running that whole time. You haven't interrupted the output.
Yeah, absolutely. This is to me where the story really starts to feel very practical. That modularity can change how something gets built and improved and all the reasons you just said there. So it makes total sense. And it's great to see it getting to that stage. We're starting to think about that. And so now that we understand the basic architecture, I'm sure everybody didn't follow every ounce of that, but I do have a much clearer picture. So that's great. I want to talk about how to measure progress. So Fusion has had this long history of maybe big promises and confusing milestones. And so it's important to be clear about what actually matters. So, fusion conversations often kind of blur terms like ignition, net energy, scientific gain, and commercial power. What scorecard should serious people actually use when evaluating progress?
Yeah, I'm glad you asked. We actually just shared a blog post about a month or two ago on this very topic of how do you measure progress from sort of the lab to something that's a scaled, affordable power source that's powering the world. And we broke it up into 5 different stages of development that are important to track. The first is showing your basic scientific proof of concept, show that you have a credible foundation that you're building on. And again, that comes back to that criterion I mentioned. The Lawson criterion is a really good way to track that in Fusion. So that's sort of number one. The next step beyond that is, can you demonstrate scientific gain? So that means get more energy out of the fuel than you deliver to the fuel at sort of a small scale level. That's been done, the NIF project that when it achieved ignition, it achieved that. But the next, which is what we're designing our machine that we're building currently to do, is get facility gain. So that's more energy out than you start with in the whole system and the whole machine. And once you do that, then you've shown that commercial power is possible, but you need to take something that, for us as Pulse, we only do, we want to show that in one cycle we get more energy out than we start with. Yeah. But then to make a power plant, we have to repeat that over and over and demonstrate net power generation. So that's stage number 4, is show positive power from the system. And then lastly, it's, to compete, you're not just making power, but you have to make power in a better way than all the other great sources of power we have today. So affordable power, which is you have to drive costs down and show that your firm power source offers a better solution than the ones that are out there today.
Yeah, absolutely. Clarity is really helpful. I think, not every milestone out there means the same thing and gives us just a better way to understand the future of fusion headlines and what to pay attention to. So you mentioned it there, Pacific has made net facility gain by 2030 a major milestone. What exactly does net facility gain mean? I think you started to describe it there, but anything else, just context that would help. And why is it a more meaningful target than, say, a one-off sort of physics result?
Yeah, so net facility gain, as we define it, is so our machine stores a certain amount of energy to start. Net facility gain means that we deliver more fusion energy out from our little cans of fuel than we start with in the entire machine. And that's important because now you're in the releasing net energy. Once you do that, to make a commercial power source, you only have to increase the amount of gain a little bit more so that, you can send it through your energy power conversion systems, turning the heat into electricity, and then you can make power and then sell it to the grid.
Yeah, really helpful way to understand the milestone. Makes sense. As you move towards net facility gain, what are the most important signals of progress that people outside the fusion field should pay attention to? Yeah,
for us, there's a few major things we'll be sharing in the years ahead. This year, one of the main activities we're working on is demonstrating that a full-scale module works. So I mentioned our system's built from many modules. The system we're building these next few years is made of 156 pulse power modules that are each the size of a shipping container, roughly. So when we demonstrate that module works as needed, it's got the performance and reliability needed for our system, then building our entire machine largely comes down to making 155 more copies of that unit. So that's a big one. I think we'll also be sharing more about what power plants look like. So how we can not just get energy out, but how we can operate reliably and affordably and build them, at scale. And then we'll also be sharing, as we build our machine to get facility gain, we'll be sharing updates on the path there. And for all of those, I think the sort of unifying theme is we believe in showing our work. The fusion is getting closer, it's moving from the lab to the grid. But as we do that, it's really important to share with the public and investors and government regulators, like, these are the major milestones we've achieved. This is, the evidence behind our claims. So we'll continue publishing lots of papers along the way there. We published about half dozen this last year.
Absolutely. It's a useful filter and gives those, something concrete to watch and helps make the field easier to follow. I appreciate you going through that. So Pacific has also described a path where pulse power can change the economics of inertial fusion. What is the economic assumption inside that thesis that you watch most carefully?
Yeah, the ways that we can make economical fusion power it comes down to sort of two attributes. One is efficiency. So our pulse power technology, which I mentioned our CTO kind of demonstrated for the first time, is impedance match Marx generator technology. It's a very, very efficient way of turning stored energy into, coupling that energy to our little targets. So we can drive extremely efficiently the targets to get very high gain. So that's sort of item number one. The second is the scalability of that architecture. So when you look at what it takes to make one of our pulse power modules, it's fairly low complexity parts made from widely available materials. It's metal, plastic, oil, and water. There's domestically sourceable materials, widely available in most places you'd want to build a fusion power plant. So I think between those two things, it's both inherently efficient, which means we can make more compact systems, and it's made from things that aren't very expensive, and supply chains can be quite scalable. As we think about powering the world, we have to think about that supply chain constraints.
Absolutely. Great points there. And I think, brings economics into the focus, which I always like bringing it back to. And, fusion obviously has to work technically, but also has to make sense financially. And the supply chains have to be there, all that as well, too. So it's great to see that, the potential of that and being able to scale financially and economically. So if you had to name the hardest remaining step between today and say a utility relevant fusion system, what is that kind of remaining hurdle that needs to be crossed? Like what are still the areas that need to happen or breakthroughs that need to happen?
Yeah, I think these next few years, like I mentioned, we're in the process of optimizing our module. Once we do that, we build a lot of copies of that. So we're putting together a machine that we'll be building in Albuquerque these next few years, on which we'll demonstrate net facility gain. So that is item number one. Is that's a serious execution challenge, maintaining quality and just delivering on that on schedule and on budget. So that's the near term challenge. I think to make commercial power plants at scale, there's two additional items you need to bite off. One is you need to design all your parts to last for the lifetime of a power plant, so something like 30 or 40 years. So that means modifying all the components of the system we build today to make sure that they will last for, if we're operating at about one cycle per, one fusion target per second, you need things to last for hundreds of millions or billions of cycles, all your capacitors and switches. So that's item number one. And then the second is you need to design your system to operate that fast, to operate at something like one fusion event per second, or one fusion target driven per second.
Yeah, absolutely. It shows, again, how many pieces have to come together. But again, those are, difficult but solvable problems as well, too. And it's a good reminder that commercialization is not just one challenge, it's a whole chain of different challenges. And so it kind of brings us from, the scoreboard to the machine itself. And the next section, I want to talk about just what has to happen really when fusion moves from a successful shot to something reliable, repeatable, maintainable, and useful in the real world. And so, that single successful shot is science. Many reliable, affordable shots start to become industry. What has to change when you move from a historic experiment to something that can run as true infrastructure?
I think it's you need to design components to last in a commercial environment for very, very long amounts of time. So it's driving the cost down, making sure that the wear and tear on those units is low enough that, they either last the full life of the plant, or they can be something that's easily and inexpensively serviced at some pretty long interval. Maybe it's once a year or twice a year or so. So that is the big one. And then I think the other one is, it's the scalability of the supply chains. It's being able to mass manufacture those components. Anything that on our first demonstration of a single net facility gain shot, we don't have to have infinitely scalable supply chains for anything in that system, but we want to be able to scale up to making 100 or 1,000 power plants per year when we're ultimately down the road when we're deploying this all around the world. And then there you have to make sure that there's no bottlenecks on any material or any choice you've made. You have to make sure that all those parts are widely available.
Absolutely. And I appreciate you kind of got into a little bit of the last question. There's definitely some additional context there that I think is really helpful. And you see just kind of where the challenge becomes very real. To me, it's also optimistic and hopeful of hey, these are solvable problems, we're talking about as we scale and grow the industry more and more. So your team, I know, has emphasized target simplification. Why are targets such a big deal? And how can something tiny become, one of the largest economic questions in fusion?
Yeah, if you think about what our targets are, so in fusion, your fuel is hydrogen. It's use these deuterium and tritium isotopes of hydrogen, which when you're making this in a power plant, those are going to be effectively free and unlimited. So that is, very, very low cost fuel. That's the big advantage of fusion. But when we put it in our system, we have to package it in these little cans and then, drive those cans to compress them and get the energy out. So you have to make sure that when you're doing that, you're not adding a lot of cost that increases your effective fuel cost. So it's very important for us that we make our little targets, those little cans, as inexpensive and simple to make as possible. And one of the major scientific precedents we build on was done at a concept called maglev that was fielded on the Z machine at Sandia National Laboratories. And when they did that, they had those little cans of fuel, which is great, very simple. But then they surrounded it with these electromagnets on the top and bottom, very close to that fuel can. And then they also shined in a powerful laser to preheat it a little bit. And that gave you a little bit of an initial nudge on the fuel. You get it a little bit magnetized, a little bit hot to begin with. And if you think about it, if you had to do that in a power plant, that would be pretty expensive and complicated to do every second. So what we did is we, as a start of simplifying that target, we showed that we can eliminate those external magnets. So we've eliminated this big chunk of hardware that sits around the target and allowed ourselves to only have a little can. And the way we did that is we had this campaign on the Z machine last fall where we designed a new target that let some of the electrical current that's driving the fuel can to be compressed to provide an initial magnetic field inside the fuel. So we thinned the can, and then the magnetic field kind of bled in a little bit, and that eliminated those magnets. So that's a major simplification and lets us make our commercial targets at much lower cost.
Yeah, it's fascinating, and it's always interesting how something that's very small can have huge impact on the economics and scale. And great example, as always, of just how the details really matter in fusion, especially. But you touched on this. So Pacific's New Mexico campus, it's planned around the demonstration system. Help us just better understand, what is happening there? What is that? What does this facility need to prove, not just scientifically, but operationally? And just, kind of give us a mental picture. What is the facility?
Yeah, it's designed to let us iterate and learn as fast as possible. So we're designing it to allow us to take one shot per day. So put one fuel can in there, drive it, measure the output with our very nice diagnostic suite, and understand everything that happened. And that doesn't sound very fast, but that's actually a really high rate of learning. If you're able to do one major experiment per day, measure everything that happened, immediately take in that information and design an improved target and go from there. So that is the sort of primary mission of that facility, is let us rapidly learn and make progress to get to net energy gain at the system level. But also, there are lots of things we can start to answer about how does a commercial power plant work in that machine. So we can look at, how do we more rapidly remove materials after the shot is done, understand wear and tear on components, and rapidly get toward our goal of getting net facility gain, so net energy out at the system level.
Yeah, it to me, thinking about that campus and that makes so much sense, and being able to just test really quickly and learn and continue to improve, and it feels like a major step from concept to execution, and it's really helpful just to kind of picture that and really see how it works and how it's coming together. And I know Pacific as well has launched a users program around the demonstration system. Why invite outside users before commercial power? And what does that reveal about how you see the machine's role?
Yeah, it's first and foremost a design to get us to that point of net facility gain of our energy mission. But what's great is that, fusion enables amazing things, and this facility is going to be unparalleled in the world, like the highest yield fusion facility in the world. And there's a lot of amazing sort of science and other commercially relevant things you can learn on that facility across basic science, understanding radiation effects on materials. This matters for things like satellites and also national security. It's just understanding what happens when you have these kind of intense, X-ray neutron environments. And it's also great because, that not only does it provide the value to us to rapidly advance on our energy mission, but it also provides early revenue, which is important for a high capital intensive industry like fusion.
Yeah, absolutely. It's a really cool idea. It makes a ton of sense again. So, we've talked a little bit through this, but fusion is often talked about as a breakthrough technology, but the energy industry has to operate in the real world, obviously, as we know. What does practical grid integration look like for fusion? And how do you design for the grid we have today rather than, an idealized grid of the future?
Yeah, this is really important for us. I mentioned we're trying to design our systems for high reliability so that it can be a really good, firm power source that's always available and can ramp up and down as needed to meet grid demand. But also sizing is very important. When you look at projects that are trying to come online on the grid today, it's typically in the 200 to 400 megawatt range. So when we're designing our first power plants, we're designing them to be economical at something like 300 megawatts or less, so that we can be confident we can add a lot of plants to the grid without having to have a lot of major transmission upgrades.
Yeah, the practicality really matters. The breakthrough technologies, especially, still have to fit into real grids and real markets. And I think the energy industry needs innovation, but also needs systems that can actually connect and operate and scale up from that perspective. So we've covered a bit of the science, the system, and the path to infrastructure. I want to, close on our last section, kind of just widening the lens, where fusion fits in the broader energy transition, what kind of workforce it could create, and what the world might look like if Pacific and the broader fusion field succeed. And I'm definitely excited to talk a little bit about that one. So clean energy has made enormous progress, but the grid still needs, as we know, firm, reliable, clean power. Where do you think fusion fits, alongside solar, wind, storage, geothermal, hydro, and nuclear fission?
Yeah, I think fusion offers, in regions that are sort of newly developing where there's not a lot of grid capacity, it can be a great source of both baseload and load following power. And also our system is pulsed. We can ramp it up and down. So it also makes a great complement in regions that there's already a lot of renewables. We can fill in all the gaps and sort of provide the firming capacity that batteries or natural gas would provide today. But we can do it at very low cost, and it's clean.
Absolutely. It's a good way to frame it, and fusion is not a end all be all, maybe a replacement. I think it's a complement to as we go and, where the future will head there, but it makes a lot of sense. I think the future grid will need a mix of clean technologies working together, as I think we've highlighted a lot on the show. But I'm thinking about the people side of it. What kinds of people will fusion need if it scales? And, why is this not just a field for PhDs?
No, we need people across all disciplines, and it's really not, it's not just PhDs. I mean, you need, people coming from the fusion research system, but you also need a lot of mechanical and electrical engineers, thermal engineers, all the things needed to build a power plant. But you also need a lot of workforce in sort of skilled technicians are going to be in really high demand to both on the manufacturing side and also the plant operations side. We actually recently held an event at the New Mexico State University grants in New Mexico focused on connecting local residents and students with career opportunities on the system we're building in Albuquerque, because there's a ton of work to do to build that system and operate it. We're hiring a lot of technicians actually this incoming months, ramping up this summer too. So that's a couple examples, but it's going to be a major source of new jobs, I think, across the board.
Absolutely. It's such an important message. I think fusion will need builders at every level, as you said, at every point, and even trades, how important that is as well. I'll ask you this. If somebody that is still in their educational phase, thinking about fusion is really interesting, I'm really intrigued. What do you think is like a good starting point? Like what's a path to entry where somebody could learn or what they should be focusing on or studying?
Yeah. Come work for us.
Yeah, there you go.
No, I think it's, like I said, you really need people across the board in all these industries. It's a lot of, welding and electricians and all that, putting these systems together and operating them. So check out our website, come talk to us and figure out, how we can work together.
Yeah, absolutely. I love that. Let's dream a little bit realistically, but thinking about the future. If we go a ways out and Pacific succeeds, fusion ramps up, scales and is readily available, and this happens, like what does the world look like that people in today's energy industry maybe aren't yet imagining clearly enough? Like what's the opportunity? What could happen?
And this is why fusion is so exciting, is that the potential is that it could be the world's most affordable firm power source. That's our mission. That's why we started this company, is we see a path to getting there. And when you do that, think about energy touches every aspect of civilization. Imagine if you had far more power and energy available, and it was more affordable than anything else, and it was clean, and you could build it anywhere. I mean, it opens up all possibilities for, industries that today can't do things because the power or electricity is too expensive become possible. So it's, just more abundance, more energy for everyone at lower cost.
It's a big vision, huge opportunity, and huge upside, obviously, if we get this right as well, too, and a very powerful way to thinking about it. I think fusion could just change not how we power the grid, but really change what becomes possible. And so I wanted to highlight that as well. How far away are we? I know it's like, how can you predict it? Maybe get out your crystal ball, but from your perspective, like how far away are we to where this is commercialized and scaled?
It's coming fast. Yeah. I mean, we have to plan as if it's happening tomorrow. It'll take a few years to build the first power plants, but we are really, really close. Our goal is, like you mentioned, by 2030, we aim to show net facility gain on our demonstrator to show that we can get net energy out. We aim to get the first power plants operational by the mid 2030s. And what's exciting about fusion is it's so power dense and energy dense. You don't need a lot of land or materials to build these systems. The S curve, the adoption should be very, very fast. As we come down the cost curve rapidly with our modular technology, it will become more and more attractive to build this. And I think, this could be something that scales up more rapidly than any other energy technology ever has, given its sort of attributes.
Yeah, it's so exciting. And I wanted to put that out there because I think it's closer than most people are thinking and imagining. So that's fantastic. So let's say looking out over the next decade, what gives you the most hope that fusion can arrive in time to matter? Like, help us have just a bit of hope. Like, what are you thinking? What are you seeing? What are you feeling?
Yeah, sort of number one is I'm every day inspired by our team. We have just the most amazing, wonderful people come working for us on this incredible mission. So I think I get renewed hope every day when I talk to my colleagues at Pacific Fusion. And and as every milestone we get on the path to getting closer to that affordable power at scale, it's just, very, very exciting and hopeful, and thinking about, we're one step closer to that ultimate goal of powering the world with the best power source ever.
Yeah, absolutely. Absolutely. So as we close here, we've talked about a lot. We understand it better. We understand the potential and how exciting it is. If you were to just have the audience walk away with one thought process or one thought from this talk, what would it be?
I think it would be fusion power is coming soon, and it's really changed from what was for a long time a scientific research project into something that is at the stage where you're really looking at the engineering and execution. So I think it's a recent development, just as of 4 years ago. And, that's why we started the company 3 years ago, that change happened. So I think it's an exciting time, and it's a very exciting field to work in. So I'd encourage people to also check out our website and consider working with us if that appeals to you.
Absolutely. Strong place in there. Hopeful closing thought. I will link that in the show notes as well, too. So go check out their website and follow them more closely. Will, thank you so much for joining us on Green Giants. This conversation gave us a clear picture of why fusion has entered a new chapter, not as a distant science story, but as an engineering, manufacturing, and infrastructure challenge that is moving closer to the real world. And what stood out to me is that the promise of fusion is not just about abundant clean energy. It's the possibility of reliable power, new industries, new kinds of jobs, and a very different way of thinking about what the energy future can become. For everyone out there listening, if this episode helped you think differently about fusion, reliable clean power, or the next generation of energy infrastructure, share it with somebody working in energy, climate, manufacturing policy, investing, or skilled trades. And as always, subscribe, rate, follow Green Giants, Titans of Renewable Energy for more conversations with the people building the future of energy. And with that, we will see you next time.
This episode of Green Giants, Titans of Renewable Energy, was brought to you by Lee Group Search. If you enjoyed today's discussion and are looking to recruit top talent for your company or find your next career opportunity in the renewable energy sector, visit leegroupsearch.com. Let's continue driving the future of clean energy together. Until next time, keep pushing toward a greener future.